I will begin with a word of prayer. So, Heavenly Father, we thank you for this morning, and thank you for these students, this opportunity we have just to meet together and study your creation. Help us to glorify you what we do, and just understand a little bit more about linear algebra together, Lord. In your name I pray, Lord Jesus. Amen. So, if you've read my notes, in chapter 4, I talk a little bit about geometry. And like my long-term vision for this course is a little bit different than what's in the notes. One of the things that I wanted to implement earlier on in this course is like some discussion of geometry. And so I'm going to do that now. I don't really have much in the way of homework to reflect this. So this is one of those rare places where like maybe this is on the test, but there's no homework on it, right? So that's a somewhat unusual case, but just to warn you, this particular story arc, I don't think I have assigned you any homework on, but I do think it's important for us to talk about it. So I just want to talk about the geometry of Euclidean space. And what I mean by Euclidean space is simply Rn. So Rn, we've been working with this a little bit. It's a set of n tuples, right? x1, x2, xn, such that the x of j's are real numbers for j equals to 1, 2, n, right? And if we wanted to picture this, well, it's kind of tough, right? Because it's n-dimensional. But a silly person could make a picture that looks something like this. There you go. So there's my picture of Rn. Yeah. And if you're willing to accept my picture, silly as it might be, you know how we have vectors. Like we have a vector v, we have a vector w, you know. I'm going to use x and y rather. We have a vector x, we have a vector y, and you know the deal. X plus y geometrically, where is it? If I was to take this and like move it up here, right? That gets to where x plus y goes. Something like this. So of course you could do the tip-to-tail vector addition like we talk in physics if you've seen that, right? Or Calc 3. If you haven't seen it, no big deal. The point is we can understand vector addition geometrically. And of course, if we talk about x plus y, and we talk about the, let's say, ith component of it, by definition, it's the ith component of x plus the ith component of y. And if we have a constant times x, talk about the ith component of that, that's c times the constant I, like that, right? So these simple algebra rules I just wrote down define vector addition and scalar multiplication, right? This is the definition of vector addition. And this is scalar multiplication. Now, I want to say a little bit more. We've talked a little bit about span. We've talked about linear independence, right? So if you have, let's say, beta is v1, v2, let's say vk, right? And we let w equal to the span of beta, right? Then if beta is linearly independent, then we say the dimension of w is equal to the number of things here. The dimension is the number of things in this basis. Okay, so I talked about a basis. A basis is a generating set. It's a linearly independent set whose span forms the space. So this is how would we describe a subspace of Rn being k-dimensional, right? It means in this subspace you can build anything in it from a unique linear combination of these vectors in the basis, right? So some examples of that, of course, we can just do like, this is just like this. W is like the span of V, where V is not equal to 0. What's this space? What kind of space do we call this? This is a what? In words, this is a line through the origin, right? This is a one-dimensional subspace. And it doesn't really matter what the context is, whether I'm talking about 2 dimensions, or if I'm talking about n dimensions, this same description holds. A line through the origin is something we can obtain by simply the span of one non-zero vector. What's that non-zero vector called in geometry? It has a name. It's called the directing vector, because it tells you the direction of the line. Get out of the way. All right. Example 2. What if we had, I'll draw it more like this. So here is, I'll draw it in 3 dimensions, but of course, actually I'll draw this. This is x1, this is x2, and by the way, here's x3 through xn. All right, so it's kind of a silly picture. All right. But suppose you have 2 vectors, right? Maybe this is v1, and then over here is v2. I'm saying both of those vectors lie in my, what is that called? It's called a plane, right? So here, if I had w equals to the span of v1, v2, is a plane, right? Or, if you like, 2-dimensional subspace of Rn. Okay? So that's one thing I wanted to just come out and just give you kind of an organized discussion of this. So we can go on, right? If I have k linearly independent vectors, I have to take the span of those. That gives me a k-dimensional subspace, right? K equals to 3, we call that subspace a volume. K equals to 4, you might call that subspace a hypervolume, all right? Past that, they're all hypervolumes past 4, but, all right, so that's one thing. The other thing I wanted to talk to you about just a little bit was the definition. If we have, V and W in Rn, then V dot W is equal to the summation I equals 1 to n of Vi Wi, right? If you like, this is V1 W1 plus dot 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 plus Vn Wn. This is the dot product, right? The dot product of 2 n vectors. We just add products of matching components, yeah? Oh, thank you, I didn't see you. Oh, by the way, when you guys leave, your homework's over here if you didn't get it in the way in. Okay, thank you. Okay, so that's the dot product. Now, we can do other things with the dot product, like the length of V is this symbol right here, which is equal to the square root of V dot V. So that's the square root of V1 squared plus V2 squared plus dot 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 plus Vn squared. This defines vector length, right? Or, as we call it in linear algebra a lot, in higher math, we'll also call it the norm of the vector. Geometrically, what this is the distance from the origin to the terminal point in the directed line segment we identify geometrically as the vector. So like, I'll draw you a 3-dimensional picture of this because that's the one place where it's most easy to see. If this is x1, and this is x2, and this is x3, you see, if I have a vector from the origin like so, right, v1, v2, v3, if I drop that down, it gives me a projection down into the x1, x2 plane, right? This point down here would be v1, v2, 0, right? And if you look at that, you can see that there's a little triangle here, right? This triangle. And here we've got V1, and here we've got V2. Now, to be fair, I should probably put absolute value there and there, because my picture is just schematic. These could be in the negative cases. So if it's negative, if the components are negative, the length of the component's the absolute value, right? So certainly I have this and that. And so this guy right here, what's the length of that? I'll make it red. This one right here, right? The length of that, let me draw some arrow here, this arrow would be the square root of the magnitude of V1 squared plus the magnitude of V2 squared. But guess what? That's just the square root of V1 squared plus V2 squared. And then, if you look at it, what's the vertical height of this soon-to-be purple triangle? This is a right triangle, right? This is magnitude of V3. That's the height of this purple triangle. So what's the length of this vector up here? Square root of the length of the length of V1 squared plus V2 squared. That gives me this guy down here, right? So that's that length squared plus what? Magnitude of V3 squared, all right? But that is exactly what I've called the magnitude of V. So I can erase the absolute value there. So this tells me the length of a three-dimensional vector. It's the square root of the sums of the squares of the components, all right? So technically speaking, I've heard, it's this mathematician I used to work with here, and when you go through this discussion, it bothered him. He's like, you don't need to do that. Because when I write that the vector length is the square root of the dot product of the vector with itself, that's the definition. And he's right, that is the definition. However, the purpose of this picture right here is to try to convince you that that definition is natural with the usual understanding of coordinate geometry. And if we break things down into a concatenation of planes which are perpendicular to one another, we can understand that length in terms of a picture like this. All right? So there's that. So geometry concerns how to add vectors, how to scalar multiply vectors, the distance from the origin of a vector. What's the other thing we do in geometry? What's an important idea? Like angle between vectors, right? So there's a theorem, which I won't prove, not today anyway, which is that V dot W is equal to the magnitude of V times the magnitude of W times the cosine of the angle between them. So we have this. If we wanted to calculate the angle between two like five-dimensional vectors, we could do it. We just calculate their dot product, calculate their lengths, and take an inverse cosine of an appropriate ratio. So this is, basically gives us definition for V and W not equal to 0. The angle between V and W is by definition the inverse cosine of V dot W divided by the product of their magnitudes, the product of their lengths, that is. So this gives us a definition for the angle between vectors. We use the dot product to define the angle between vectors in n dimensions. This works for 2 dimensions, it works for 3 dimensions, it works for 13 dimensions, because the dot product is defined in all of those. One other thing I should mention, which is that we say V is perpendicular to W if the angle between them is 90 degrees, which is equivalent to saying that V dot W is what? I heard a 0. I'll accept it. This is 0. So perpendicular vectors have dot products which are 0. We use that as the definition. Geometrically, it means there's 90 degrees between them. Or pi over 2 if you're partial to radians. Not me so much for this discussion. Finally, one last thing in this diatribe of geometry is we can define the perp to a subspace. Like the perp to W, what that's going to be is all x in Rn such that x dot W, let me do it the other way, W dot x, it doesn't matter, the dot product is commutative by the way, W dot x is equal to 0 for all W in big W. So this is the perpendicular to a subspace. All right. We'll talk much more about this towards the end of the course. I just want to introduce the concept here, just to try to give an interpretation to some of the calculations we're doing. All right, so let me just do one angle calculation, then I'll get back to what we were doing last time. Let's see here. Example, what am I on? 3? All right, so here we go. Suppose you've got V is the vector 1, 1, 2, and I don't know what we got here. Square root of 3. And W is, let's say, 0, 1, 0. Let me put a 2 here, and I'll put a 0 over here. All right, fine. If that's the case, let's calculate the magnitude of W. What is it? To me, the magnitude of V is what? Square root. 1 squared plus 1 squared plus 2 squared plus the square root of 3 squared. What's that? Six plus 3, 9. So the answer is 3. Incidentally, point of order. If on the test you come to something that's like the square root of 16, or the square root of 25, or the square root of 9, or the square root of 1, please simplify. Otherwise, it hurts my heart. So, that's not so much an issue in here, but in college algebra, like there's like not simplifying obvious things like 3 over 3. The answer 3 over 3. What do you do? Like, do you not know? It's very unsettling for me. I don't know why people do this, but anyway. Okay, so the length of W, 0 squared plus 1 squared plus 2 squared plus 0 squared, also known as, looks like square root of 5. This one doesn't simplify, right? What's V dot W? We do 1 times 0 plus 1 times 1 plus 2 times 2 plus the square root of 3 times 0. So the dot product of V and W is apparently 5, right? Great. So then the angle between V and W is, by definition, the inverse cosine of V dot W over the magnitude of V, the magnitude of W. Do you see why they have to be non-zero, by the way? What's the length of the 0 vector?
0.
0, right? So we don't want to divide by 0. So that's why we have to have non-zero vectors here to define the angle between them. But my V dot W was 5. And I've got like 3 over the square root of 5, right? And so whatever that works out to, if I have my calculator, we'll find out. So while I'm, aw man, left my calculator in my office. Anybody have a calculator on there? It's a race. Who will get to it first? I'd like degrees, possibly. What's it got? Well, I mean, what's the angle, though? Oh, yeah. Is it really 42 degrees?
41.8.
So 42 degrees, then. Fine. Close enough. Okay, you said it was actually 41.8, but I'm making it 42 for the sake of... Haha, that's funny. I would point out, we just found the angle between two vectors that we cannot picture. Right? Can you draw a picture in 4 dimensions? I mean, you can draw my silly pictures, right? That are just kind of schematic, but see what algebra has done for us? It's allowed us to calculate the angle between vectors that we can't actually just directly do in terms of, pen and paper, compass stuff, protractor. Yep. What is it? No? Okay. So in view of all this, example 4, if W is equal to, let's say, the span of the vector 1, 1, 1, 1, find, basis for the perp to W. So I'll tell you a theorem of linear algebra, and the theorem is simply this. W perp is equal to the set just containing 1, 1, 1, 1 perp. In other words, if I find all of the vectors which are perpendicular to the generating set of W, that's the same as finding the set of vectors which is perpendicular to every vector in W. This is true because, well, in this case, every vector in W is just a scalar multiple of that one vector, 1, 1, 1, 1. All right? Okay, so what equation are we up against? We're trying to solve the equation 1, 1, 1, 1, dot with x1, x2, x3, x4, right? Equal to 0. Also known as what? x1 plus x2 plus x3 plus x4 equals to 0, right? That's what this equation is. That's the equation we're up against. So actually, if you look at this, well, we can write down the solution immediately, right? We have x1 is equal to minus x2 minus x3 minus x4, right? So if I call this thing x, my solution x has the form minus x2, oops, well, you guys couldn't see it, but I wrote a comma where I meant to write a minus. x2 minus x3 minus x4. x2 is x2, x3 is x3, x4 is x4. All right? I wanted to find a basis for W perp, right? So what I currently have is just a description, a parameterized description of an arbitrary point in the perp. All right? To find a basis, I need to, here's the calculation. Factor out x2, and we start with minus 1, 1, 0, 0, plus x3 times minus 1, 0, 1, 0, plus x4 times minus 1, 0, 0, 1. Let me give these things a name. These vectors that we just found, I'll call this one V1. I'll call this one V2. I'll call this one V3. And in summary, the perp to W is the span of those three vectors, V1, V2, and V3. So the space which is perpendicular to this W, right? What is W? W is a line through the origin in 4 dimensions with direction vector 1, 1, 1, 1. Yeah, 4. What is the perpendicular to a line in 4 dimensions? It's a volume, right? This has got 1, 2, 3 linearly independent vectors. So the space which is perpendicular to a line in 4 dimensions is actually a volume, right? What we'll generally understand is, if you look at a space and the perpendicular to the space, it's going to fill the totality of the ambient context. Here the ambient context is R4. So if I'm looking at one space as one-dimensional, if I looked at the perp of that space, it has to be 3-dimensional because the total dimension of both of these put together has to match the 4. But anyway. So my larger point is just this. If we go back to what we were doing last class, we can understand finding the null space of the basis for the null space of a matrix. What that means geometrically is we're finding like the basis for the space which is perpendicular to the rows of the matrix. All right, anyway. Enough about the geometry. Let's get back into the thing we were doing last time. We should do some more of those. Unless you guys have a question, you can jump in with a question at this point if you have one. Like, let me just repackage my last example, which was what? Example 4. So example 4 reinterpreted. Remix. Find basis for the null space of A equals to 1, 1, 1, 1. So like the null space of A is equal to x in R4 such that AX is equal to 0. But that's, you know, let's talk about this. AX equals to 0 is the same as what? 1, 1, 1, 1 times x equals to 0. Right? But here, let me expand. What is x? X is a 4-dimensional vector, right? So that's actually x1, x2, x3, x4. But that's exactly the calculation we just looked at, right? Let me put this a different way. There's a side comment I should have made, I don't know, 20 minutes ago. Comment. V dot W is also equal to V transpose times W for V and W in Rn. So we can write the dot product as a row-column multiplication. That's what the dot product is. It's the product of this row vector times this column vector. See, this is a 1 by n, and this is an n by 1, which goes to show you that the dot product is a scalar. Okay. Anyway, my point to all this is simply this, is we've already figured out that the null space of A is equal to the span of those vectors we found, v1, v2, v3, which I'll write again here. I guess I was writing them this way, minus 1, 1, 0, 0, is that right? Minus 1, 0, 1, 0, and minus 1, 0, 0, 1. Yeah? I didn't actually look at the other board. I wrote those down by just thinking. Think about this. You want vectors, right? That when you take the dot product of these vectors with the rows of the given matrix, which in this case there's just one, the dot product has to be 0 for this to be a legitimate answer, right? Is the dot product of this vector with that 0? Yeah. This with that? Minus 1. Every time it's minus 1 plus 1, which is 0, for all three of these respective dot products with the vector 1, 1, 1, 1. Okay. Maybe this example is too simple. Let's look at another one. Example 5. Let's suppose that we have A equals to 1, 1, 1, 1 minus 1, and I don't know, 0, 1, 1, 0. All right? I want to find two things. I want to find the basis for the column space of A, and also I want to find the basis for the null space of A. Both of those are answered if we calculate the reduced row echelon form of the matrix. Why didn't I calculate the reduced row echelon form of the matrix for example 4? Did I need to? No, I didn't need to. It was so simple I could just write down the answer, right? Although I did try to write the answer down in the standard format, which is to use the non-leading variables as the parameters of the solution. There was one pivot. It was corresponding to the x1 column, so I wrote x1 as a dependent variable of x2, x3, and x4, for example. Here, I do need to do a row operation, right? So what do I got to do? At least one. What we got here? Row 1 minus row 2. I think we're done after that, right? I think that's the end of the road, right? This is roof. This is the reduced echelon form of A, right? Agree? Yeah, I think we're done. What are the pivot columns? Again, yeah, 1 and 2. So these are my pivot columns. So we go back here. CCP says, okay, column space of A is the span of the pivot columns. So my basis for the column space, most naturally, just use 1, 0 and 1, 1. The truth of the matter is, guys, here, this is a horrible question for me to ask on a test because there's almost nothing that you can put down for your answer of the basis for the column space, which is wrong. As long as you have two vectors, which are not linearly dependent, when you take the span of two not linearly independent vectors, what is the column space of A actually equal to? Think about it. It's the whole of two-dimensional Euclidean space. So like, this is a hard question for me to grade in the sense that I can't really say you're wrong. There's so many answers here you could give. But the natural answer to give is the span of the pivot columns of A, all right? How about the null space? The null space requires a calculation. So to find the basis for the null space, X is in the null space of A, right? Means that AX equals to 0, which means that, what do we get from here? We get X1 is equal to X4, and X2 is equal to minus X3. And X3 and X4 are free. But that's not the answer, because we're trying to find a basis for the null space. All right, we're trying to find a basis for the null space. So this tells me that X has the form what? It's got X4 for X1. It's got minus X3 for X2. It's got X3 for X3, and it's got X4 for X4. All right? So then I can factor out the parameters. This gives me X3 times 0 minus 1, 1, 0, plus X4 times 1, 0, 0, 1, apparently. So this all tells me that the vectors I just found there, we can use these as a basis for the null space. So the null space is, in fact, the span of this vector, 0, minus 1, 1, 0, and 1, 0, 0, 1. And this right here is basis, because it's a linearly independent spanning set, which makes it a basis. So the null space here is two-dimensional. The column space is two-dimensional, but they're very different contexts, right? The null space is a two-dimensional subspace of four-dimensional space, right? Whereas the column space is just literally R2. We can check our answer again, guys. See how this works? The dot product of this vector, 0, minus 1, 1, 0. What is it with this? You got zeros hitting the outside numbers, right? 1 minus 1. So you get 0 with the first row. How about the second row? Zeros with the outside numbers, and 1 minus 1. So if you check the first vector there in my basis, the dot product with the first row and the second row of A are both 0. the second vector here, 1, 0, 0, 1, take the dot product. Again, we get 1 minus 1 and zeros in the middle, 1 minus 1, 0, and over here, the dot product, everything in the dot product's got a 0 in it, so the dot product is 0. So indeed, my basis for the null space is perpendicular to the rows of A as a check on the calculation. And also as a meaning for what the null space is. It's calculating a perpendicular space to the rows of the matrix you're looking at. Any questions? Let me show you another one, I guess. Here, let me use the notes for a bit. I got some more complicated examples in the notes that will take me longer to write out, so let me use some of my previous efforts on this matter. Aw, man. Oh, there it is. Got too many cables up here. All right, so like here is a similar but more complicated example. This is on page 129. This is in chapter 4. Now, by the way, guys, like chapter 4, most of it is relevant. It would be good for you guys to read it. There's one section I don't expect you to understand or to process, and that's section, I think it's 4 point. There's one that's on vector spaces in the abstract. That I'm not covering in here until much later. So you can kind of skip that section if you want. It does have like general theorems about vector spaces. Reading that may give you an intuition, which is useful, but I don't require it, okay? Because our focus is just on Euclidean space and subspaces of Euclidean space in here until like the last day or something. Okay, so anyway, just saying that there's a section in chapter 4, which I don't really expect you to read. I think it's 4.5. By the way, 4.6 is good. There's some examples in here which are helpful to us. So here's a matrix, and I'm asking the question, find a basis for the null space of A, all right? So we do the row reduction, and you get this, all right? To find the basis for the null space, all we do is we take this and we write down the corresponding homogeneous equation solutions, right? So like this first top row tells me that x1 is equal to minus x4. This guy tells me that x2 is equal to x4 minus 1/2 x5. And this third row tells me that x3 is equal to 1/2 x5, right? So the reason I'm seeing that is, remember, ax equals to 0. If we concatenate, if we like slap a column of zeros on the end here, we have the same row reduction, right? So we can kind of do this little trick to solve the homogeneous problem without actually writing down the column of zeros. And then finally, x4 is x4 and x5 is x5. I then put those equations into the generic x, right, like that. And I factor out the parameters, x4 and x5. The vectors which result, those form a basis for the null space. All right? So here the null space is two-dimensional. All right? What about column space? I don't talk about it here. Let's add this to discussion. What would the basis for the column space of this matrix be? What are the pivot columns? This one, and that one, right? So by the column correspondence property, we can use the first 3 columns of the matrix for a basis for the column space. Now this example is much like my last one. The column space is kind of silly because we're talking about three linearly independent vectors in R3. What that means is that when we take the span of the columns, the first 3 columns of the matrix, we get all of 3-dimensional Euclidean space. All right? Do you guys see the pattern here? What's the dimension of column space? What's the dimension of the null space? The dimension of the null space is the number of non-pivotal variables. It's the number of non-pivot columns. What's the dimension of the column space? It's the number of pivot columns. every column in the matrix is either a pivot column or not, right? So what does this mean? This means that the dimension of the column space plus the dimension of the null space has to be equal to what? Not 0, no. The total number of columns, right. This is what we call the rank nullity theorem. The rank nullity theorem, by the way, nullity is a fancy word for dimension of the null space. So the nullity is the dimension of the null space. The rank, by the way, is the dimension of the column space. Probably should write that down if I had a marker. Rank of A is the dimension of the column space. The nullity of A is equal to the dimension of the null space. All right? And the rank nullity theorem says that, by the way, this is equal to number of pivot columns, right? And this is equal to the number of non-pivot columns. And then finally for A in Rm by n equals to the rank of A plus the nullity of A. This is the rank nullity theorem, which seems like an exceedingly silly thing to point out if we're just talking about it with respect to row reduction, right? But it is saying something, right? It is saying something actually kind of interesting, because you understand that the column space and the null space, they're actually in different spaces, right? The the null space is a subspace of Rn, whereas the column space is a subspace of Rm for an m by n matrix. And this is saying that there's some connection between those two spaces, and it has to be that the sum of their dimensions is n. By the way, notice once more that if we take this vector, right, and we take the dot product of this vector with any one of these rows, we get 0, right? Like I get -1 plus 1 is 0 for the top one, right? This one gives me -2 plus 2, and then zeros, right? That's dot product of 0. Dot product of this with the fourth one, I get -4 plus 4 plus 0 plus 0 plus 0. And this one also, if we take the dot product of this vector with all three columns, it's 0 each time. All right? So we can check our calculations for the null space basis if we simply take a second and take the dot product of our alleged basis with the rows of the vector we just solved. Any questions? Do you guys understand the algorithm? I have another example if you want to see it. This one's kind of silly. Here you have this is a rather silly matrix, right? 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1. I probably didn't say the right number once, but you get the idea, right? This 3 by 4 matrix. We can do the row reduction pretty quickly. It's just going to give us this, right? You subtract off row 2, row 1 from row 2, row 1 from row 3. We get the reduced echelon form, right? All right. What's the rank and what's the nullity of this matrix? Can you tell me? Rank is what? 1. What's the nullity? 3. Very good. So notice that if we solve for x1, so like think about this. This means that x1 is equal to minus x2, minus x3, minus x4. The free parameters here are x2, x3, and x4. So if I have ax equals to 0, that means I can write x as what? I can write x like this, right? And this is the basis for the null space. You can easily see that every one of these vectors is perpendicular to the 1 1 1 1 vector. Yeah. And in fact, you could have guessed these. Once you start seeing what we're doing, you don't technically even need to go through this if you really understand what's going on. A sufficiently with it student could just write the answer down. I totally think that's possible. But you don't have to do that because there is a straightforward calculational procedure, which is to row reduce the matrix and simply write down the equations for the homogeneous solution in this fashion, factor out the non-pivotal variables. The vectors which remain have to be linearly independent because of the structure here, and as such they form the basis for the null space. Now, this one, the column space is actually kind of interesting. What's the column space of A? You guys told me it was one-dimensional, right? What is it? What's the direction vector for the one-dimensional line, which is the column space in R3? Yeah?
1, 0, 0.
No. So that's the thing. The column correspondence property says we use the pivot column of A.
So 1, 1, 1.
1, 1, 1, right. Right idea, wrong matrix. So, but yeah. And you can see that too, right? Every column here is just that vector, right? So if you add any linear combination of those, it's still just a scalar multiple of that 1, 1, 1 vector. So geometrically, the column space here is a line in 3 dimensions, right? So I keep talking about geometry today, partly because there's a lot of you who feel, you will feel better about the course. You'll feel like you're doing something if you have some kind of like geometric understanding of what's going on. Does that actually help you solve problems? Sort of, but not entirely. All right. You can also talk about row space. The row space is the span of the columns of, The row space is the span of the rows. I'm not really testing on that this semester, at least not now, but there is something to notice there. Okay, so next time, let me show you what we're going to talk about next time, guys. It's like an appendix. This is the so-called LU factorization. So it turns out that you can take any matrix, well, you can take most matrices, and you can do the forward pass on them we talked about, right? The forward pass, in other words, clearing out below the pivot positions, all right? If you do that, you can get to a matrix that has, zeros under the pivot position. That necessarily is an upper triangular matrix. All right? It turns out that if you keep track of what you did, you can understand that A is equal to what? I mean, this U is equal to what? It's equal to the product of the elementary matrices on A, which achieved this row reduction. And if you tilt your head and squint and look at that, it turns out that when you solve that, that gives you A equals LU, where L is a lower triangular matrix and U is an upper triangular matrix. So this is the so-called LU decomposition. It's actually a major topic in linear algebra. I'm not just doing it because we're at Liberty. But next time I will show you so like this one, the L happens to be this. If you take this matrix times that matrix, you get back to the A that I had here. Anyway, next time I will show you a slick algorithm for calculating the LU decomposition. Don't forget your homework back here if you didn't get it already, guys. Thanks, everybody.